measuring enthalpy change, aka calorimetry. Okay. So at the end of the previous video, we did a calculation question where a sample of food went through combustion to heat up 100 ml of water. Via heat transfer, we were able to measure the enthalpy, essentially, of the combustion of those food. Okay. So the general idea behind calorimetry is just like that. Okay. So first of all, we're using ethanol to heat up the bunch of water on the calorimeter. Okay. So ethanol goes through combustion reaction in the burner. Then the energy released is used to heat up water in calorimeter. So by calorimeter, we literally just means that it's an insulated container used to measure enthalpy of a particular reaction. Water absorbs heat then, and therefore rise in temperature, which can be read from the thermometer. And in the end, we have a relationship between the enthalpy of the reaction and the enthalpy that's absorbed by water. Okay, so the enthalpy of the combustion reaction takes place in the burner. The heat then released theoretically is absorbed by water to increase temperature. So notice that there is a negative sign in the equation, which speaks to the direction of heat transfer. Combustion reaction releases heat energy and water absorbs that energy. In a school setting, you're most likely to encounter a calorimeter. A solution calorimeter. It can be made with double-layered styrofoam cups, a stirrer to make sure energy is evenly distributed throughout the thermometer, and we can use it to measure the enthalpy of, for example, neutralization reactions, which tend to be exothermic, or a metal displacement reaction, which also takes place in a solution. So for combustion reactions, the bomb calorimeter provides a better insulation compared to the setup we saw before. Okay. Under ideal circumstances, heat produced by the reaction is transferred in its entirety, and we could expect to see data recorded below. Temperature versus time on the graph, right? At the instant where reaction starts, temperature starts to increase, and therefore we could obtain the delta T, which could later be used using specific heat capacity of water or whatever liquid that you're using for your experiment. However, we all know that ideals are just ideals, like when we thought our summer will go versus how it actually turned out when COVID rampaged. Okay, so reality barely holds up to expectations. It's a lot of times a lot more complex. So in your experiment, you're most likely to get this. So because heat loss happens during the entire reaction, the maximal temperature we record won't be the actual maximum. By the way, how do we know that heat loss actually exists? Like here, the declining temperature suggests heat loss. Okay, so we need to back extrapolate the time when reaction starts. So that temperature there for the maximum temperature, when we back extrapolated, that account for heat loss in a better way. So when asked to evaluate and suggest for improvements, here are some commonly referred factors for this particular calorimetry experiment. First of all, not all heat produced by combustion reaction is transferred to water. Remember, there is never a perfect insulation. Even if we back extrapolate our data, there will still be heat loss unaccounted for. Okay? The combustion of the ethanol, if we use ethanol or whatever liquid that we use as a fuel, is unlikely to be complete owing to the limited oxygen available based on experiment. Okay, so compared to the literature value, we always have a lower heat of combustion. The experiment also wouldn't really be performed under standard conditions. So as a result, our data sort of like has compromised in accuracy. Okay, so when you are asked to evaluate experiments like this and suggest for improvements, Please remember, avoid giving trivial answers such as, oh, there is incorrect measurement. Honestly, what do you mean by incorrect measurement?